Okay, good afternoon, everybody. Welcome. Welcome to College of DuPage. I'm Paul Servatka. I'm the president of the Chicago AMS. And so we have some AMS people here. I know it's kind of an odd time for a meeting, but this is going to be a great presentation. We have COD AMS with our president. Yay, Taylor. And other people too. They're all happy. And then we've got some students coming in here and some people from Unidata and the National Weather Service at various offices from around the country. So this is a very exciting talk today. I'm going to introduce to you Dr. Eric Bruning. He is from Texas Tech University, and he is really one of the leading experts in thunderstorm electrification, as well as being able to understand this GLM, the geostationary lightning mapper. And he's worked closely with some of us here at COD, with Mike Zaransky particularly, to try to get some of the products that you'd seen on the screen that display that lightning data that's coming from our orbiting satellites, the geostationary orbiting environmental satellite, or what we call GOES. And so I'm very excited about Dr. Bruning coming to talk today. He is a graduate in many degrees from the University of Oklahoma. He's actually a Midwestern boy. He came from Madison, right up the street. And now he's living in Texas, and he knows where, and he works close to where Lubbock's, Kegel's Steakhouse is, which is one of our Storm Chasers' favorite places to eat. So Lubbock is a great place. Texas Tech University does a lot of great research. They've been responsible for things such as the Texas Mesonet and a lot of wind, some of the wind work. And what's the name of the TTU or?
So there's a National Wind Institute, and we have the Debris Impact Facility that was responsible for a lot of the civil engineering work to establish debris indicators for the enhanced Fujita scale.
Excellent.
So that's one of the things we're famous for.
So if anybody's interested in kind of a fun hands-on university where there's a lot of field studies and experiments and doing actual data analysis, that'd be a great place to go. But I'm very excited today to welcome Dr. Eric Bruning.
Well, thanks for having me. It's a real pleasure to be here at College of DuPage. I'm actually going to switch out of the formal presentation here and just for a moment share my gratitude for this fabulous resource for the community. Those of you who are students may or may not be aware just how widely used and beloved the College of DuPage website is across the country for real-time weather data. I have it on good authority from some fairly high-level forecasters in the Weather Service that they can't officially request it, but getting these products onto the College of DuPage page was one of the early requests because it is so widely used even by the pros in the Weather Service. So you have here on the to prove this is a real-time data feed. Of the product I'm going to be talking about, some of the geostationary lightning mapper in the blues and in the brighter colors on top of the channel 2 visible from the GOES ABI. I am personally responsible for all of those lightning pixels and the code that makes those pixels appear there. So we'll talk a little bit about that later and sort of how these products came to be. Yeah, you can see a couple areas of lightning with convection reinvigorating here. Probably from a decayed convective complex. I haven't really looked at the weather much today, but that's kind of what that looks like. And then a lot of subtropical convection out over the Bahamas and into the east. Pretty good flash rates there, actually, in that one cell. You notice that early on here, there's not lightning, and then it suddenly appears. That's an artifact because NOAA had a GLM outage today, and just in time, the feed came back. So, yeah, I don't think it was my code. So. All right. Let's get into the talk. I'm indebted to a bunch of people from NOAA and the meteorological research community and Weather Service for the support and actually operationalizing these GLM products that I'm about to talk about. Probably should have put Mike Zaransky and a few others on the slide here too, given the setting, and but definitely a huge team effort to make this come about. The GOES-R series of satellites, which began with GOES 16, you can see in the upper right corner there, which has the ABI, the visible imager and infrared imager that we're all very familiar with. There's a bunch of space weather instruments on there as well. And maybe the most interesting new thing for the meteorological community was this geostationary lightning mapper instrument that you see on the bottom there before they packaged it up on the satellite. It's one giant telescope that sees almost the full disk of the Earth. And so we'll talk about how that works in just a moment here. But I promised you some meteorology, so we're actually going to start in the cloud and how storms become electrified, and start here with this story of where lightning begins, and that's in the mixed phased region of clouds, where the temperature is below freezing and down to minus 40 Celsius. Electrification takes place when fairly small ice crystals, maybe even a little bit smaller than that size range that I said there, begin collecting these supercooled water droplets, and they rime and turn from snowflakes into these rimed particles called graupel. This is a scanning electron microscope image on the right here of what that rimed surface actually looks like. And when these rimed particles, these graupel particles, collide with other ice crystals in the presence of supercooled water, storms electrify collision by collision, and then we can start talking about making lightning. So that's what the rhyming process looks like close up. This is actually a photo from my office window in Lubbock, where we do sometimes get snow. And we actually had some graupel precipitate on this day, and so you can see the characteristic conical shape here of the graupel particles. That's for the same fluid dynamic reasons that the Apollo capsule is shaped the way it is. It's the sort of stable accumulation and flow field around that ice particle. And you can see lots of regular stellar crystals and even smaller fragments of ice crystals here. And so it's precisely these things that are in the mixed phase region of every thunderstorm that are colliding with one another, and you get about a picocoulomb of charge on individual particles that winds up in about a nanocoulomb of charge per cubic meter. So tiny units. All right, so the supercooled water in thunderstorms, that's present in the updraft region of the storm, where there's updrafts typically in excess of 5 and up to 50 meters per second. In a supracellular thunderstorm that leads to an abundant production of this supercooled water that leads to the formation of these rimed particles. And as I talked about, there's a mix of graupel and ice crystals. And so you can see graupels here, the circles, and then these ice crystals marked by the stars. And this electrification process also depends on temperature. So once we have the supercooled water content, in the warmer part of the cloud, the graupel is going to electrify positively, and the ice crystals that are colliding with the graupel will electrify negatively. And then above some reversal temperature line, which is about minus 15 Celsius, but varies a little bit. So in the colder part of the cloud, the electrification polarity flips, and we get negative electrification to the graupel and positive charge on the ice crystals. And then once that precipitation, if the updraft subsides, or if the precipitation is sheared out of the updraft and detrains, those larger graupel particles will precipitate just like any other precipitation, and the ice crystals, which are fairly small, will remain lofted in the cloud. And together, those two regions of electrification combine into these 3 net regions of charge that you see depicted here. So typically a pretty strong mid-level negative charge region in the thunderstorm, and then an upper positive charge center, typically maybe around 10 kilometers or so, and then a lower level positive charge center that's primarily graupel, and it's actively precipitating, so that one tends to be a bit weaker because that charge is continuously precipitating out of the storm. All right, so once we have this basic net electrical structure, which is not all of the things that the charge structure can be, but it's the most basic unit of electrification we have in thunderstorms, you can then get you can get lightning discharges that will begin in the strong electric field region between each of those pairs of charge regions. So there's roughly then, in a typical thunderstorm, 2 altitudes at which lightning can initiate. If it initiates between the upper pair of charges, the yellow circle there, then we get an intracloud discharge, most commonly with a negative channel that moves upward into positive charge, and a positive channel that moves downward into negative charge. So the lightning is going to neutralize the electrical charge and reduce the electrical stress. And then in the lower pair, you get downward negative leaders into positive charge and an upward positive channel into the mid-level negative charge in the storm. Sometimes those are intracloud discharges, but most commonly these lower level initiations will come to ground as a negative ground strike. All right, so this is what typical lightning looks like. You also notice this big tall tree that comes out of the top of the cloud, and this is a special bolt from the blue discharge. Sometimes there's so much negative electrical charge in the mid-level regions that it can't be neutralized by going upward and leaks out the side of the cloud and comes to ground out the side of the storm, and those tend to be a big surprise. So we've sort of adopted the colloquial term bolt from the blue to have this sort of technical meaning for lightning flashes that do that. Positive ground flashes are another story entirely. Most commonly, those are actually produced by storms that have an electrical structure that's flipped over from this for reasons that I'm not going to get into right now. We've had whole field projects just studying that one question. And there's actually still a lot of fundamental uncertainty on how electrification works and how we can actually predict the electrification rates and polarities from the observed environmental conditions. All right. This is another depiction of what I just showed you. The shaded regions here are these 3 charge regions with the small lower positive charge, and here we have an intracloud discharge that's starting in the region between those 2 charge regions. The smoother contour lines are electrical potential. And you remember from your physics class that it's the gradient, the derivative of the potential that's then the electric field. And so this is the large electric field region here where there's a dense packing together of these potential lines. And so it's that electrical potential energy that's built up by the charge that is then discharged by these lightning discharges. And one of the things that tells us then is that sort of like how mass adds up to gravitational fields, the electrical charge adds up to the potential fields. And it's actually exactly the same mathematical laws that describe that. All right, so is charge always layered in storms? It turns out it is not. And so the picture in the upper left is sort of the textbook version that we give you to start with. That is easy to get your mind around. But if you do a high resolution simulation with electrification in a cloud model, this is some work a previous master's student of mine, Matt Brothers, did. He's now in the Weather Service. On the left here, this is the actual charge structure inside this fairly simple ordinary air mass multicellular storm. And you can see how complicated that is. And that's because the fluid motions in the updraft, you're familiar with this when you look at a cumulus cloud, it's very bubbly and turbulent. And so the charge is advected around on those very small scales and acquires this very complex structure. On the right is the electrical potential. So after we add up the effect of all of those individual charges, that's a much smoother appearance, and it actually gives us this simplified structure that we give you in the textbooks. So you can sort of reason from the electrical potential a little bit more easily than you can from the actual charge structure. And if you had a simple charge structure, it would have a simple potential structure, but not necessarily vice versa. All right, so again, just to put this in the thunderstorm context, this is a supercell in West Texas with a very obvious updraft here and the very turbulent cloud. And then as we reach the level of neutral buoyancy, that anvil develops and spreads out, and that's a much smoother, lower textured cloud. And next time you see a thunderstorm, you can just look at the texture of the cloud and actually picture the complexity of the charge region matching the complexity of the texture of the cloud. Also, a little advertisement for Texas Tech. In addition to our debris cannon, we also have mobile radars, and so we're out in the field with those. We have a set of deployable meteorological sensors called stick nets that are on surveyors' tripods that we also deploy for severe storm studies. They're rapidly deployable. So yeah, lots of good observational work at Texas Tech if you want to get into grad school. All right, one more thing about different storm modes. We already mentioned this sort of simple air mass thunderstorm, or more properly, a multicellular thunderstorm. And it primarily has this updraft, downdraft process that we all learn about for how thunderstorms work. And that's pretty much the only thing it does. The updraft goes up, the precipitation forms, and it falls out. So it's a sort of one-dimensional structure. If you go to more complex storm modes, like a squall line or a leading line trailing stratiform mesoscale convective system, these systems have an intense updraft along the leading line and, of course, the heaviest precipitation rates that you see along a squall line. And those are going to have that same electrical structure that we've already talked about. But then in the mesoscale updraft, in the stratiform region, back behind the updraft, there's a much, much more complex charge structure that results from a mix of additional electrification that happens slowly back there and charge that's being advected from the leading line into that trailing stratiform region. Again, this is another case where there's going to be this sort of turbulent charge structure that adds up to about 3 net charge layers here in the leading line. And then in the trailing stratiform region, we're going to get these much more layered charges. And this is where very extensive electrical discharges can develop in these very smooth, extensive charge regions. And then finally, maybe everyone's favorite storm mode is the supercell, long-lived, isolated cell. And that has a characteristic 3-dimensional structure, right? It's rotating. There's precipitation falling out in the rear flank of the storm and in the forward flank of the storm. And that complex flow structure is also then reflected in a charge structure that can vary in the updraft core and then towards the forward flank. Actually, this is towards the left flank of the updraft here, and then towards the forward flank on the right here. Again, your meteorological intuition about the complexity of these storm modes maps very nicely onto the complexity of the electrical structure. Okay, so now you know where to find charge in storms and something about how it's organized. It's complex in the updraft. It's smooth outside the updraft. And we'd like to compare that structure to lightning mapping data. So let's first talk about radio frequency lightning detection. Here's a photo a graduate student took of a bolt from the blue cloud to ground CG flash. And the National Lightning Detection Network, or Earth Network's Total Lightning Network, are really focused on detecting these cloud to ground strikes. These are the kilometers long, tens of kiloamps in strength, high current charge transfers that come to ground, and those are very easily detected by a radio frequency, a lower radio band radio frequency detection system. Recently, those systems have also gotten more sensitive, and they're starting to detect more radio pulses that are produced by intracloud current flows. And so if you see the upper part of a cloud flickering, there's some current that's flowing up there too, just like you would have in a ground strike, but maybe a little bit lower in magnitude than these big ground strikes. A newer instrument that's been around since about 2000 is what's called a lightning mapping array. And these lightning mapping arrays work in, actually it's old analog TV channel 3, so 60 to 66 megahertz. And that means there's lots of parts available for doing nice filtering of the radio signal to capture just that band. And it's also a nice radio quiet place where the only thing that sits there is lightning. And these systems take advantage of the precision of GPS timing to allow us to locate through time of arrival triangulation where individual steps in the lightning channel take place. So every time a lightning channel steps, we get a little pulse of VHF radio noise. And we can locate that many, many times because computers are fast now. And from that, we can build a three-dimensional map of the channel structure. So this is actually the lightning mapping array detection of this same ground strike here. And color indicates time. It starts in blue and develops towards green. And you can see it branching as it comes towards the ground. And then after it makes ground contact, there's some of these warmer colors, which is additional processes responding to that ground strike all the way up in the cloud. All right, so this research data was a big part of the justification for GLM because we suddenly had this sense of all of the different things that channels were doing in clouds, and we could see what's called total lightning, which is all of the electrical activity in the cloud, and also something about the extent of these channels and how they fill the volume of the cloud. All right, so let's talk about GLM then. What is it detecting? I mentioned these pulses of light that we're all familiar with seeing with our eyes when we watch a thunderstorm, and that's exactly what GLM is looking for. GLM is a 500 frame per second camera in space that looks at the full disk of the Earth continuously and detects the pulses of light that are produced by these large current flows along lightning channels. So large current flow, the channel lights up, it makes a pulse of light that lasts about 2 milliseconds, which is why we have a 500 frame per second camera. And we look at this very narrow band at 777.7 nanometers, which is near infrared. So just beyond red here. And this is actually the location of an oxygen spectral line. So if you want to get into the weeds of radiative transfer, I'm not sure how far you students have gotten into that yet, but there's individual elements will light up a little bit extra in certain colors, and that's what we see here. And GLM optimizes its ability to pick out these light pulses from the background by looking specifically for these spectral emission lines. All right. So this works both day and night. We can pick out nighttime. It's kind of easy to imagine that this works, but it also works during the day by looking for subtraction. You subtract out the bright cloud background and look for the extra photons that are produced by lightning above that bright cloud background. And you can still get about 70% detection efficiency during the day, actually a little bit better than that. So it's important to know, we talked about these radio networks detecting these strokes of lightning. GLM's optical detections are not always going to line up with those, and that's actually a challenge for operations, which is what do I do with these lightning data sets that are detecting different parts of the physics, and how do I synthesize those together? And that's, again, an open area of sort of research to operations, and operations to research is our friends in the Weather Service ask us for clearer guidance scientifically on what to do about these things. All right, so how does the GLM detection actually work? It's a camera, so it has a pixel grid that's detecting these photons. And some terminology I want to introduce here. Each individual flicker of light is what in the GLM data is called a group. And that's because it's a group of pixels that are illuminated in one frame that are close to each other. So little pools of light that are little splotches on the detector array. Making up those groups are the individual pixels, which are called events in the GLM data set. And then groups that are close together in space and time are grouped together, clustered together into lightning flashes. So there's an algorithm that runs on the satellite data automatically that generates a data set that is events, groups, and flashes. If you want to go pull off one of these data, our friends at Unidata make sure that NOAA's data feed gets disseminated out to the academic community and really to the public. So you can go grab these data files off of Unidata's website, and or now a cloud. The cloud, there's an Amazon Web Services bucket that has all these data in real time as well, and this is actually what the structure of the data file looks like. There's a level, basically a data table of all the flash information, all the group information, and the event information, and then numbers that link together the events to their parent group, and then the parent group, or the groups to their parent flashes. So it's this tree that's represented as 3 data tables. All right. So this is what we're going to make use of, and you can just see from looking at this tree of information that sure doesn't look like the images that I opened this talk with. This is a good thing to disseminate from a data provider point of view because it reduces the information down to just the absolute bare minimum. But for practical display, this doesn't do us a lot of good. So we have to reconstruct what these lightning flashes look like using an additional algorithm. So the process is to take those lightning flashes and all of the associated pixels that are illuminated by each lightning flash and add them back up to emulate the original detector array that actually did these detections and turn that back into images. Because the GLM is a telescope, just like the regular imager has a telescope. It sees things from the same point of view, and the look angle from the satellite to where things are happening on Earth is identical for GLM and ABI. And so we actually restore all of the GLM detections back to their original satellite coordinates so that when you get a GLM image and a visible or an infrared image, you can stack them right on top of one another in a very naive way, and everything lines up perfectly because that's exactly where things originally came from. And so displays like this are pretty much what the Weather Service is now using day to day in their operations for looking at this satellite imagery, and it's what you can get on the College of DuPage website. This one has a sort of white color map to make it look a little bit more like lightning, but you can color map it any way you want. And I'll show you some other color mappings in just a bit here. If you want to access the imagery files, Unidata also is serving out the Weather Service feed to the public, and so that's also available on Unidata's website. It's actually not quite an official satellite product. We had to sort of backdoor it because it wasn't part of the original plan for GLM. And then, well, we realized that this is what we needed to do for operations, and so we made it happen. Also, if you want to start with those events, groups, and flashes and run the code to make the images yourself, you can run exactly the same code that the Weather Service is using to make these images. It's an open source package called GLM Tools, and that's available on GitHub, and you can go grab it and the public data feed and make your own products. So that's fun. You can go look at how I wrote that, and you probably won't like it. I don't like it much anymore either. It's an accumulated series of skill and understanding over the years, and anyone who has ever written code will tell you that you trust all your old code because you've used it a lot, but you may not like it after 10 years as it accumulates a lot of detritus. Technical debt is the term there. All right, what are these 3 products? There's 3 products that we make for the Weather Service. What are they? The real foundational product is one that we call flash extent density, which is simply the count of flashes that pass through each pixel in the image. So in a thunderstorm core, you might have 10 lightning flashes in that thunderstorm core, and then off to the side, one big flash that illuminates a bunch of pixels in the thunderstorm's anvil. And so that's what this flash extent density is. It's easy to think about. It's right there. There were 3 lightning flashes. The other product that's pretty straightforward to imagine is one called total optical energy, or TOE. This is the total light that's emitted, and so this is basically what your eye would see. It's an accumulation of the total light, and is not much more to say about it beyond that. And then we also have this product called minimum flash area, which visualizes the area of the smallest lightning flash passing through each pixel. And this is a really complementary product to the flash extent density. In high flash rate regions, we tend to observe small lightning flashes because those small lightning flashes are taking place in the thunderstorm's updraft, where there's a high rate of electrification and a very turbulent cloud that's chopping up all of that charge into small pockets. And so that then leads to smaller lightning discharges. And so it gives forecasters confidence about what they're interpreting in terms of the convection by having this pair of flash area and flash extent density products. You're probably ready to stop looking at a data table though, but I'm not going to give you that yet. I'm going to give you product construction information, and then I'll give you a pretty image. All right, so let's, I've got two lightning flashes depicted here, and then I'm going to sum them up to give me this, this final grid. If you think about each lightning flash, it might flicker, like in this top one, 5 separate times. And so in some spots, it's going to flicker 5 times, and then other parts might only flicker once in that same lightning flash. And so you can see the core of this flash has 5 pixels that were detected that illuminated in separate time frames. And then out here, there's only one. Flash 2 only maybe had, it looks like two groups, and so its event count is a little bit lower. So 43 total individual pixel triggers in this first flash and 14 in the second flash. If we look at what that looks like on a flash extent density grid, it's just, was there lightning there or was there not for that flash? And so it's just +1 for each pixel that had a flash go through it, and that's what you see on the right column. And when you add those up, this flash extent density product will have a value of either 1 or 2 because there were only 2 flashes, or 0 where there was no lightning. And then we can also calculate an event density grid or a group extent density grid, which is what you have on the lower left corner. That's not used operationally though, so we can forget about that from here on out. All right, so how do we work with this operationally? The GLM data come out in little 20-second chunks, and we can accumulate those however we want. And from some testing in the National Severe Storms Laboratory Hazardous Weather Test Bed and other tests at forecast offices, we determined that forecasters really liked the availability of frequent updates in these products, so a new image every minute. But longer accumulations to stabilize the relative intensity and the visual continuity of thunderstorm cells. So it still flickers a little bit, but not quite as much as it would flicker if you had a 1-minute accumulation. And then different centers might prefer different accumulation times. So in a severe storm setting for a supercell, that 5-minute accumulation is plenty to accumulate a good visualization of what that storm's doing. But for things like the FAA, where they're monitoring aircraft flying past storms over open ocean routes, they just want to know, where's there a thunderstorm? And so a longer accumulation that gives a real stable picture of the extent of electrified cloud is more of what they prefer. And these products are pretty easy to take. From the 1-minute frames, you add them up into 5 minutes or add them up into 15 minutes. And you can sort of stack the images together mathematically very, very easily. So it's very flexible for the Weather Service in that way. On the right here, I have a 1-minute and a 5-minute version of each of the 3 products. And so let's first look at the red arrow here. And you can see how in flash extent density, you have a very high flash rate here in the convective core, and then maybe just one lightning flash that was a real big one that illuminated that thunderstorm's anvil. And that pairs up nicely, as I promised you, with a relatively small minimum flash area associated with that convective core. It's a little bit more interesting to look at the orange arrows here, and there's this very low flash rate region. There's not an obvious storm core and flash extent density there. But you notice if you look at the minimum flash area, there's individual little patches of smaller flashes. And that suggests there's probably a fairly extensive charge region there, but still some weaker updrafts bubbling underneath that anvil umbrella. And so this is one of the things we like about minimum flash areas, that it adds this additional interpretive layer to the what you would get out of just a raw flash count. Total optical energy, again, it sort of looks like light. In the top right corner, you can actually see how it, in the 5-minute image, maps out what looks like the shape of an individual lightning channel. And I'll show you another example of that in a little bit as well. If it's close to the cloud top, it's gonna have that branching, snaky path, and that's the part that's lighting up. And so if it's close enough to the cloud top isn't going to blur that as much, and you'll actually see the path of the lightning with it. All right, let's talk about a longer time period here. This is a long loop starting with the end of a day, and it's on top of a thermal infrared image. So we're seeing the land surface cool off at night here. The color map's inverted, so the clouds are in black. And then at sunrise, there's a little glint artifact that happened. And now this is over the Amazon basin, and a bunch of thunderstorms popping up over the day during as the land surface is heated. And then you see the leftover anvils, and it's really great to have the lightning data in situations like this that are complex scenes to know where the active convective cores are. You can look at thermal IR imagery and get a sense of that, but this makes it real obvious where those deepest, most obvious convective cores are. So in parts of the world where there aren't radar networks like we're privileged enough to have here, this is extremely important because you can now get a much better sense of thunderstorm nowcasting with this sort of form of a kind of radar from space. It's not really a radar, but it allows you to see similar cellular structures related to the thunderstorm updraft. All right, here's now a squall line, or really a mesoscale convective system. This is from some early hazardous weather test bed trials. And actually, in the course of those trials, we originally tried out an average flash area instead of a minimum flash area. And we learned that we could actually maximize that convective core signal by taking the minimum instead of the average. And so we switched to that in response to forecaster requests. Here we have a decent amount of lightning in the high reflectivity region. You can see lightning sort of stretching out along that whole convective line. And then back behind it here is one very extensive lightning discharge. It actually looks like it's more than one lightning flash in the flash extent density here. And that's because the algorithm is accidentally chopping up the individual components of the flash because it doesn't quite meet our assumptions. So algorithm work is hard. But notice that the average area of that flash, or the minimum area of that flash, is very, very large, and it really dramatically illustrates the difference between this the flashes in the convective core and this extensive, many hundreds of kilometers long single lightning discharge that happened. Yeah, those are. Paul just mentioned here, those are the crawlers, and if you've ever seen that on the underside of a storm, that's exactly what's being mapped here. World record is, I think, about 750 kilometers, and that was established using the GLM. Over South America, I believe that one was, and then there was the duration record is in excess of 10 seconds. I think it's closer to 15, something like that.
Really quick question.
Yeah.
Real quick question. Are they always, or are they primarily on the stratiform range side, or do they go to the forward flank? And you get these long anvil crawlers ahead of the system?
It's the stratiform range side primarily, but in places like supercells, you'll also get, where you have a lot of charge going into the forward anvil down shear, you'll get, you do get sufficient charge advection that direction that you can also get anvil crawlers out that way too. Yep. All right, and then in optical energy, this is another example of where you can actually see the path of the channel itself. And if you actually connect the dots on the centroids of the individual groups, it maps out a whole fractal flash skeleton that you can kind of visualize. All right, back to a little bit of science here. Lightning is most common in the mixed phase region of the storm, and that also turns out to be one of the areas of cloud physics where we have the greatest uncertainties. And so lightning is an interesting new data set from a research point of view because it gives us an opportunity to assess how mixed phased updrafts vary using a tool that's different from, say, polarimetric radar or satellite remote sensing, other satellite remote sensing approaches. And then, of course, it's of great operational relevance since the updraft drives all these other storm processes. And so in addition to my sort of research to operations hat that I wear and helping out the Weather Service with this product, I also have a bunch of active work ongoing to apply GLM data and other lightning mapping data to see how we might use it to better understand how storms electrify, and ultimately what we might learn about mixed phase microphysics. If you think about trying to understand the climate system, one of the greatest areas of uncertainty in climate forecasts is in their representation of clouds. And the greatest uncertainty in the clouds is in these ice phase clouds. And so there's a great opportunity, I think, here even to use lightning on the global scale to help better constrain mixed phase cloud microphysics in a way that helps to long-term improve climate models. And so that's why, for instance, the US Department of Energy, that does a bunch of work in clouds and climate, has been interested in adding lightning to some of their field campaigns recently. We'll also use a new tool this summer to look at lightning very, very fast with cloud microphysics using polarimetric phased array Doppler radars, which are just now becoming available. University of Oklahoma has a couple of these at C-band and S-band that we'll be trying with lightning data for the first time. And that'll allow us to stare with a vertical cross-section in RHI at the storm and basically update that scan continuously and watch the cloud microphysics evolve and how the lightning is moving with respect to that to those clouds. All right. You might have also, if you have, this has made it to the press even at times, heard discussion of lightning jumps, and this was work done by Chris Schultz for his PhD at University of Alabama, Huntsville, using lightning mapping array data as a proxy for what the GLM might be able to show us. And Schultz defined lightning jumps as a statistically significant increase in flash rate above the sort of background fluctuations in flash rate that were happening in a storm. And one of the things that he also pointed out is that during a lightning jump, you also tend to see, and the lightning jumps in the red here, this is flash rate now in a vertical cross-section. In these increases in flash rate in the upper part of the storm, that also corresponds to relatively small lightning flashes, just like we've already talked about. And so this sudden increase in flash rate and a decrease in flash size is a really reliable way of detecting a significant invigoration in a mixed phased updraft. All right, so we've put that into play in an operational setting and used that to inform forecasters about how they might add lightning data to their conceptual model of storm processes that they're already familiar with from looking at fluctuations in reflectivity. So if the updraft goes up, it's going to make more precipitation, and the red thunderstorm core will get bigger and more intense, right? We're all familiar with that from watching the radar. And similarly, flash extent density will do the same thing. So you can watch inside this white box here, and flash extent density, you'll see a sudden increase in flash rate in the core of the storm, and at the same time, the average flash area or the minimum flash area will go down. Not much to look at in total energy in this one, so you can ignore that. But watch this play through. There's a data outage. That's fun. All right, so there's the core, and then right there's a jump in the flash rate, and then the flash rate subsides. And if you watch the area panel, that you'll see the flash area is sort of moderate, and then it's going to go down right through here, and then we'll get larger again towards the end of that updraft pulse. And so this sort of pulse in updrafts, you can actually see then visualized nicely in this flash extent density image. So this is useful in severe weather warning operations. If you're wondering whether an updraft is sustaining itself, it gives you additional confidence on top of your traditional radar interpretation that a thunderstorm is maintaining its intensity, or you might choose to not continue a warning if you see the flash size is starting to get big and the flash rate's going down. All right, let's see, some more details about the instrument. So we want to apply these kinds of techniques across the United States. And it turns out that GLM has a variable detection efficiency as you go across the continental United States. So this is a depiction of the detection efficiency for goes east for GLM 16. You can imagine flipping that image around, mirroring it left-right, and that would be then the detection efficiency for goes 17 from the, or now goes 18 from the goes west position. But what this plot is actually showing is the minimum detectable energy. So you think about those optical energy plots, what's the smallest pulse of light that we can detect with the GLM. And this is sort of the fundamental sensitivity of the hardware. It's a little bit better at night than during day, which makes sense. There's less noise we have to get rid of during the day, so we're a little bit more sensitive at night. And then you can see that it's decently uniform across most of the eastern U.S., but then you get out to, let's say, my home here in Lubbock in West Texas, and we have this then gradient out towards the Pacific Northwest where, yeah, you can see maybe the brightest lightning flashes, but you're really cutting off a lot of your sensitivity. There's also these streaks going across here that really stands out. Those are actually due to a very low-level hardware thing. Those happen on the boundaries between the different subarrays in the detector array, and there's some things that are happening there that actually lead to greater sensitivity on those boundaries that I'm not going to get into. But that's actually evidence of the hardware itself showing up in this sensitivity plot. You can calibrate this relative to another somewhat more sensitive instrument, the Tropical Rainfall Measuring Mission's lightning imaging sensor, which was a low Earth orbit version of this instrument that flew from 96 to 2015, I think. It was a very, very long mission, and so we built up lots of statistics of what lightning looks like. And so Ken Cummins, who also helped invent the National Lightning Detection Network, did some work to cross-calibrate those two instruments and convert this minimum sensitivity into a flash detection efficiency. And so this, you can see from this graph that at about a 5 femtojoule, which is 10 to the minus 15 joules, at that 5 femtojoule threshold, you lose about 50% of the lightning flashes. And so this gradient region here has about a 10% detection efficiency penalty per femtojoule. And this is really important for operations, right? If you're at a Weather Service office in Florida and then you transfer to Wyoming and you apply your sort of rule of thumb for what's a strong flash rate, you're actually missing a bunch of flashes in the data set that you were used to seeing down there in Florida. So again, this is what we worry about as scientists and engineers, to try and give a good calibrated data set. You can actually make an image of this sensitivity in real time by adding up the minimum energy in any pixel that the GLM detected. And you can see both the diurnal cycle, this change from dark blue colors in the northwest part of these images to more yellow colors, which is higher detection efficiency as the sun sets and the instrument kind of comes out of its sensitivity minimum during the day. This is actually a prototype that we're working on as a sort of data quality product for the Weather Service so that they can make use of this fundamental sensitivity information in real time and know if the instrument is performing at maximum sensitivity or if it's a little bit less where they're working. Another thing that happens is that storms have lots of hydrometeors in them, and you've all stood outside in a thunderstorm when it's pitch black, even though it's the middle of the day, and that's because a lot of the light from the sun just can't make it through the clouds. Well, the same thing happens for lightning inside the cloud trying to get out of the cloud. And in the most severe storms, they have lots and lots and lots of ice crystals. And those are causing optical extinction. The light is getting absorbed as it's trying to go out through the cloud. And that also reduces the sensitivity of the GLM. And so this is a real big challenge because you want to think that as my ice production in the cloud is going up, the flash rate would keep going up, right? That's what the fundamental physics says should happen. But because the ice also interacts with the light, now your detection efficiency actually decreases and can sometimes be almost completely extinguished in the most severe storms. So this case that I'm showing you here was in situ validated by a forecaster at the Lubbock office as having a lot of ice in it. So here's a giant hailstone. And we have a lightning mapping array that we operate in West Texas that showed there was absolutely a maximum in lightning, just as you would expect. The radio signals aren't absorbed in the same way. They're they go right through all that precipitation. So we can see all of the lightning with our VHF instrument, but notice that you barely see any lightning in the corresponding time here in the GLM data. And so this is another operational challenge. How do our forecasters make use of lightning data when in the most severe storms things fall off? And in fact, this is exactly what we tell them to look for, and we tell them to compare it to the traditional ground networks that still will have a lot of lightning. And so if you see flash rates in the ground networks go up and GLM go down, you actually have evidence that you have a more intense storm because you're seeing less lightning, counterintuitively. All right, here's another example of that. West Texas is sort of in that gradient region of fundamental sensitivity, and we have severe storms with lots of ice. And here's now a detailed view. This is Lubbock County here, and lightning detected by the lightning mapping array. Bottom panel here is a map view. And then in the top panel here, this is a time height view, where I've also marked the times at which GLM detected lightning. And you can see that it's somewhere between 12 and 25% of the lightning flashes are detected by GLM, and the other 75% are missed due to a combination of these two effects that I've been talking about. This is also stuff that I have a master's student working on, and also looking at ground network data and further trying to fill out this picture for the Weather Service of how to work with these lightning data sets together. Characteristically, if you're looking at some of the GLM imagery, it winds up having this kind of speckled appearance that you see here. Instead of big pools of light, it's just 1 or 2 pixels that manage to have enough light, and so it looks a little bit more speckly, and that's another characteristic of these reduced detection efficiency cases. All right. Stepping back even further, I mentioned the application of lightning to studying ice microphysics on a global scale, and I mentioned the TRIM-LIS instrument, from which we use to make a global climatology of lightning in the tropics. And you can see in this top panel here how the land areas wind up dominating the global lightning production, because the land surface gets heated and can make deep convection that way. Out over the oceans, there's much less lightning, although there's a maximum, for instance, over the Gulf Stream and in the intertropical convergence zone, and even downwind of the continents a little bit. So this is sort of what the global pattern of lightning looks like in the tropics. And that took 16 years to build up, and in only 1.5 years of GLM 16 and 17, you can reproduce much of that basic pattern. And to the so we're now building up a global and continuous climatology of lightning with these new geostationary sensors. That's really exciting as well, because the European Weather Satellite Agency, EUMETSAT, just launched their 3rd generation Meteosat system that also has a lightning imager on it. So friendly competition between global powers leads to a proliferation of new lightning mapping instruments, and that makes me happy. And over the course of the next year, we'll start to get the first data from this lightning imager that will cover Europe and Africa, and a good portion of Brazil as well. And we'll actually be using some of GLM data to compare the relative sensitivity of the European instrument to the US instrument. In fact, I'm going to be at a meeting at EUMETSAT next week to talk about our plans for doing all of that work. They're going to, I think, take a lightning mapping array to Lake Victoria as well, or maybe South Africa. I think those plans are not totally sure yet, but they're going to take a lightning mapping array, we hope, to Africa to also do some of these validation studies in a region that has lots and lots of lightning. The Chinese have also launched what's a prototype lightning imager on their Fengying 4A satellite. That imager only had a limited field of view over mainland China and over the South Indian Ocean and the western half of Australia. That I've never personally worked with any data from that, but you can see the seeds here of a global constellation then of total lightning mapping. And as it says there in the title, the World Meteorological Organization has recognized the value of lightning data on a global scale and has declared it, I think it was in 2018, one of its newest essential climate variables, which provides then sort of programmatic authority to coordinate lightning mapping efforts across the world, to harmonize our flash detection sensitivity, to build up a reliable climatology so that we can use it on these climate scale studies. Remains to be seen how lightning will respond in the climate system. And one of the reasons why I can't give you a really good statement about that is because those mixed phase microphysics are really hard to get right, and they're hard to map onto lightning. And so there's good PhD level work in trying to figure out how to use lightning properly as a good proxy for use in improving climate models. So that, I believe, is where I will leave it for today. I'll wind up here once again with thanks to College of DuPage for making it so easy to put together this last slide yesterday morning when we had the system going off the east coast of the US. And now you know what to do with these 3 products that you can pull up on the COD webpage. Not only can you find the convective cores here, but you know what these low flash rate regions are, and you know to go look at the flash area data, and you can see these big blue blotches that are big extensive discharges happening out over the Gulf Stream. So that is where I'll wind up, and I'd be happy to answer all your questions.
So we do have time for some questions, so please feel free. Just raise your hand, we'll get you a microphone. I know, well, here, while we're doing that, I know I can start. Some of the images you had where the flash rates were blinking faster than the image satellite underneath it.
Yeah.
What is the temporal output on the flash rates? Because I think we've matched, Mike, have we matched ours to the image that we recreate? Or can we upgrade the temporal?
So you're talking about the temporal resolution of this?
Yes.
First of all, Eric, amazing talk. Thank you so much. If I understand the question right, it's like we saw in the talk, forecasters often prefer 1-minute updates, the high resolution updates, but they want a 5-minute aggregation so that you can kind of level out these details, right? On the COD website, the way this works is the satellite imagery is the base for time comparison. What that means is for continental imagery that updates every 5 minutes, you're only going to see those 5-minute updates because there's really no intermediary base image to change throughout that time frame. On the mesoscale imagery, that updates every minute. So it's still a 5-minute aggregation, but that's where you'll see the 1-minute update is on the mesoscale imagery because that imagery is updating every minute. In some cases, the powers that be can put both mesoscale sectors in the same place, and now you have 30-second imagery. I'm not going to lie, that plays a little bit of trickery with some of the time matching that takes place, especially with the point flash data. I don't know that I've looked terribly close at the gridded data to see if that has some of the same little trickery, but if they go into 30-second mode, it will still update every 30 seconds. It just might have a weird artifact to it. Does that answer the question? Okay.
Yeah, and we don't make 30-second gridded lightning imagery products. We could. In fact, you can make a gridded imagery product at the individual frame scale and restore the 500 frame per second images. I've done that for the other thing GLM detects, which was a fun surprise, which is bolides, which are meteorites that enter the atmosphere and explode, and they also look like lightning. And the meteorite community is thrilled because they now have a public data set that they can use to look at the full field of view and they've actually, I think, used this to go like chase down meteorites that have happened, and they're also just building up a much better climatology than they've ever had.
The criticality of our infrastructure, the very foundation, the basis of your reliable form of climatology is people, correct?
Certainly,
Yes.
people do the work to detect
I was
these
just
things. Yes.
suggesting that that the information be in an introductory level to have lectures, classes for people to be spotter awareness, etc., on the earth, online, to call in. A lot of people don't even know that. They look at it and keep driving, walk. They don't know it's a lightning spark and the sort. It'd be classes for spotter awareness or lectures or classes for people. What are you doing with your harmonizing a reliable form of climatology and using people getting that information out, people reporting, including half of the world's population, including even in citizenship classes, that we need to, in order to help assist in minimalization of those fire strikes and the drought, etc., we need to reach out more for people to report it, to be aware of, to be a spotter and the sort. What are you doing for your reliability form of climatology to include the overall population?
Of course, yeah. So the public infrastructure that does this work, and the public education infrastructure that disseminates understanding of these kinds of things, places like College of DuPage that are maybe a more accessible and affordable form of education than a research university might be.
In order to extend it to 50%, 100% of the population, what are you doing for that? Because I'm seeing that this seems primarily for meteorologists. We need everybody on the foundation of reporting.
That's right, and
That's
that's why I think-
everybody. And we need them on the
Absolutely.
ground to call in instead of driving by and saying, oh, isn't that nice? They need to be aware and be spotter awareness and the like. That's what I'm saying. Okay?
Absolutely.
Exactly. Not just for meteorologists, but a common human everyday. It should be in the citizenship classes. It should be in basic. It just needs to be, because if we report these early, you know the essentiality of that? That's critical. The meteorologist is one of the last to get it, but that format between A and B can be minimalized.
Yeah, if
by
I
the
could
reporting.
if I could jump in here just as a kind of as a statement too, a lot of work that's going on here with the lightning mapping, in addition to the climatology systems, this is being used by National Weather Service forecasters to have a better understanding of when to issue certain warnings. I mean, lots of things are being changed in that. And what's really happening is you're taking it away from the necessity of spotters to understanding the improvement in the sociology of getting early warnings out. So I think a lot of this is, how does a forecaster expect larger hail or perhaps tornadoes as its storm is pulsing up or something?
Yeah, absolutely. And that public warning infrastructure and public participation in Weather Service activities through storm spotter activity is wonderful. And for the audience in this room, it's a lot of students and the next generation of people who can serve the public and work with the public to use data like this and to know how to have a sound interpretation of what's here in the public resource that the College of DuPage provides through their web services.
So I do have two questions for you, more in my specific understanding. Is number one, when we have flashes, like we're not on some of the GLM stuff, but just the flashes, how is that flash location being identified, and how do you separate the flash location from the actual long bolt?
Yeah, so if you like look in the data files, you'll get a latitude and a longitude for the flash, and that is it's the center of the pool of light is what's being recorded there, because that's what we have to work with. So we take the weighted average of the optical pulses and report that as the center of the flash location. It's really valuable to pair this with the ground strike network data sets, because those are really tuned to locating the points of ground contact more so than this is.
Now, with the LMA, the Lightning Mapper Array, you said something, and I just wanted to clarify it. It's only detecting around 25% of the actual lightning flashes, the GLM?
Flip that around. So the LMA are all the colored dots there, and the LMA sees a lot more than the light green lines, which is the GLM.
Oh, okay. So are those just smaller flashes intra-cloud, or?
Yeah, that's an excellent point. So there's a systematic increase in the sensitivity as you go to longer duration and more spatially extensive lightning discharges. Those are tapping into more electrical energy, and so they're brighter and they're better detected by the GLM. If we had an infinite sensitivity on the GLM where we could count like one photon, we might see all of these tiny little sparks, because a lot of times you can see them with your eye, things that are not super bright like those anvil crawlers, but they are generally too dim for the GLM to pick up when they're, 100 milliseconds long or something like that.
Do we have some other questions from even some students or professionals?
So with the, first of all, great talk. Thank you so much. And my question is, with the detection efficiency somewhere between 12 and 25%, are you discouraged by the relatively low number compared to, let's say, comparing it to NLDN or any of the other ground-based networks? Or are you seeing this as a monumental triumph that, hey, we're getting this and it's working and we know we can do a lot better?
Yeah, it's a triumph. I think the sensitivity of the instrument actually exceeded what was sort of specified when we built it. And so we're still seeing, in excess of 70% of the lightning globally when you average across things, across time and space. The other thing that we got out of the GLM that we weren't totally expecting is that it was really built as a flash detector, and we hoped to just be able to get a detection for each flash. The sensitivity has been good enough that we've been able to do some of these channel mapping things that I showed you, so we can actually now look at the spatial coverage of lightning, and that's driving a lot of excitement now for, there'll be a new version of this instrument on the next generation geostationary satellites, and looking at improvements to sensitivity to further improve that mapping capability.
Follow up to that, you talked about GOES 17 now. We're into GOES 18 for the West Coast satellite. Are you seeing, was there any improvement done to the mapper at all, and are you seeing any results from that?
Yeah, absolutely. So I mentioned the master's student that's looking at these data sets, and it's pretty clear over West Texas, and this will translate elsewhere, that GOES 18 is a little bit more sensitive. They learned a lot from the first two instruments, and were able to make some adjustments to how they built the instrument and how they, especially on the electronics and optics side of things, to improve the sensitivity. And so it's not like we're seeing twice the number of flashes, but it's a noticeable improvement as well.
Is there, for the students here who maybe in the next 20 or 30 years of their career, what are you planning on improving as the GOES constellation moves forward?
Yeah, that's a great question. I think better sensitivity to see some of these smaller, shorter-lived lightning discharges would be my first request in these supercell storms where we have very, very high flash rates. The things you most need to detect to watch that fluctuation in the storm intensity is going to be those smaller, shorter-lived discharges. And so anything we can do to increase our sensitivity of that would be my first request. I think we also always like more resolution, just because more resolute pictures are fun to look at. And so getting GLM to a point where you can have resolution that's closer to the ABI, where there's sort of a one-to-one correspondence between the ABI pixel and the GLM pixel, might give you a little bit more detail of the light. And we've all seen this with our eyes, right? You go out and you see lightning, and you can see the cumulus turret being illuminated by that, and how cool would that be to see that from space? Now, that's harder to convince Congress to go up and take pretty pretty pictures. So, but the sensitivity of the instrument and the ability to do that go hand in hand, because you can, as you make the pixels smaller, you count fewer things, but if you can make the instrument sufficiently sensitive, you can keep making those pixels smaller too.
He'll have a question. And in line, one more really quick question. You said it's the just beyond infrared and the near infrared. Is that the optimal place to detect the lightning, or have you fooled with other wavelengths?
Yeah, you can. There's papers from the 70s that looked at this, like prior to the Liz instrument, to choose this as one of the more sensitive spots to do this. There is a European research instrument that's looking at that UV, so 334 nanometers. And that's a little bit more sensitive to the channel development itself. So it's a sort of purplish plasma color instead of the bright high current flows. And so you can actually see slightly different things in that band. And that's one of the other things that people are looking at right now. Yeah.
Yeah, my question was about that graph you showed where it correlated the number of crystals in the updraft to the density of the flashes, and then you got to that critical point, yeah, right there where it actually drops off. Is there any plans to maybe get around that, or what does the future of that look like? Because as you mentioned, you know, to have that problem fixed would be very useful for forecasting and warnings and all that.
Yeah, I guess I'll keep reiterating the sensitivity point, right? There's still photons there. They're just being extinguished and probably not fully extinguished. So we should be able to restore some of this with increased sensitivity. I think also synthesis maybe with the ground networks and trying to look at an integrated lightning data set would also be a helpful way to work around that, and having, you know, maybe some modeling from reflectivity that you would say, we expect there to be more extinction here from the radar, and synthesizing all that information together to get a sort of best estimate of the true flash rate. Yeah.
We'll take one more question.
So my question would be about high atmospheric lightning, or I believe it's transluminescent electric events or something like that.
Yeah.
Would there be a chance that you guys would be taking a look at that, because it would be stronger storms that would usually produce those, to my knowledge?
Yeah, there has been some evidence that GLM has seen transient luminous events. That's things like gigantic jets and blue jets. Those blue jets are actually a little bit easier to see in that 334 nanometer band I mentioned. And so the Europeans have been looking at that with the research instrument quite a bit. But we have, there are a few reports now of GLM seeing gigantic jets and so forth. You can see them from the International Space Station too, where you have astronauts are flying just, you know, with a camera looking out towards the edge of the Earth, and you'll see the discharges come up from the tops of storms. Yeah.
Okay, well, once again, thank you. That was fantastic. This is something I've always been not very good at, so great to have you here. So thank you very much. For the AMS people, this is our last scheduled meeting. If we can find something to do, maybe even over the summer, we will certainly schedule that in. But thank you all for coming today. Thank you. Have safe travels back for those of you leaving, and the rest of you, we'll see you later.
Thank you all.